Hi, hello, welcome to Trinath chemistry classes. In this video, I am going to discuss about intermediate second year chemistry topic, electrochemistry. In this electrochemistry topic, this is my fourth video. This is my fourth video, part 4 of electrochemistry. In first three parts, I have discussed about what is electrochemistry. Electrochemistry is a branch of chemistry which deals with the conversion of electric energy into chemical energy and chemical energy into electric energy. The branch of physical chemistry which deals with the conversion of electric energy into chemical energy and chemical energy into electric energy. Based on the ability of a substance to allow the flow of electrons or passage of current through it, substances are classified into two types, conductors and insulators. Conductors means which allows the passage of current through them are called conductors. Again, these conductors are classified into two types. Conductors are classified into two types, electronic or metallic conductors. Second one is electrolytic conductors. Second one is electrolytic conductors. Here, conductors are classified into two types. One is electronic and another one is electrolytic. We have seen some differences between electronic and electrolytic. There is no chemical change here. No chemical change. Here there is a chemical change during the passage of current. Here chemical change is there. Here conduction is due to flow of electrons. Here conduction is due to flow of ions. So we are going to discuss about electrolytic conductors. I have divided electrochemistry into two parts. Electrochemistry into two parts. One is conversion of electric energy into chemical energy, and second part is chemical energy into electric energy. Chemical energy into electric energy. I have started the first part, conversion of electric energy into chemical energy. Electric energy into chemical energy. The device which is used to conversion of electric energy into chemical energy is called electrolytic cell. We have discussed about construction and working principle of electrolytic cell in my first three videos. Then we have discussed about what is electrolysis and what are the products formed. Products formed at cathode and anode. Formed at cathode and anode during electrolysis. Cathode and anode during electrolysis. The products formed at cathode and anode during electrolysis also discussed. Then we have solved some numericals. Based on the Faraday's laws. Faraday's laws gives the quantitative relationship between the amount of reaction occurred or amount of substance deposited during electrolysis and the quantity of current passed through it. Those are Faraday's laws. The Faraday's first law of electrolysis and Faraday's second law of electrolysis. We have solved some numericals on those Faraday's laws of electrolysis. Then in third video, I have discussed about resistance, conductance, then specific resistance, then specific conductance. And we have discussed how to determine experimentally the resistance of a metallic conductor. The resistance of a metallic conductor is determined by using Wheatstone bridge method. We have discussed about resistance, then conductance. Resistance is the ability of a substance not to allow the flow of electrons is called resistance. The ease with which a substance allows the flow of electrons is called conductance. And resistance of any metallic conductor. Resistance of a any metallic conductor is directly proportional to its length and inversely proportional to its area of cross section. Then from this we have brought one more word, that is specific resistance. So specific resistance is the resistance of a metallic conductor. Specific resistance is the resistance of a metallic conductor whose length is 1 centimeter and area of cross section is 1 centimeter square. That is called specific resistance. Then we have brought one more word, specific conductance. Specific conductance. So this is denoted with kappa, which is nothing but 1 by rho, reciprocal of resistance. We have seen how to determine the resistance of a metallic conductor or conductance of a metallic conductor. The conductance or resistance of a metallic conductor is determined by using Wheatstone bridge method. Wheatstone bridge method. Wheatstone bridge method. Wheatstone bridge method. In Wheatstone bridge method, there are 4 arms. There are 4 arms. 2 arms are connected to the known resistance. Third one is variable resistance. Its resistance can be varied. And the fourth one is unknown resistance, whose resistance is needed to be determined. You see here in Wheatstone bridge method, like this, there are 4 arms are there. So this is known resistances R1 and R2. This is R3 is variable resistance. I have already discussed. If I have like this, shown like this, this is corresponds to resistance. If arrow is there, this is corresponds to variable resistance. Then this is the R4 is the known resistance. 2 arms are connected to the galvanometer. The rest 2 arms are connected to the battery. Rest 2 arms are connected to the battery. When the bridge is balanced, the current flowing through galvanometer becomes 0. At that condition, which is said to be balanced, R1 by R2 is equal to R3 by R4. If we know R1, R2, R3, we can determine the R4 value. We can determine the unknown resistance value. Unknown resistance value. So once if we get the resistance, we can determine the all other parameters such as conductance, specific conductance, we can determine for any metallic conductor. Later on, we have discussed about how to determine the conductance of a solution. Conductance of a solution. For that, we have designed a special cell that is called conductivity cell. We know we have already discussed this construction. Conductivity cell consists of 2 platinum wires. At the bottom of this platinum wires, there are platinum foils will be there, and entire these things are kept in a glass vial like this. It is fixed, and here it is also fixed. Here the distance between the platinum foils is 1 centimeter, and the area between these 2 platinum foils is 1 centimeter square. This is 1 centimeter square. Right. So the 2 arms are connected to the like this. The 2 arms are connected to the 4th arm of the Wheatstone bridge method. Again, we start changing the variable resistance until the current flowing through galvanometer becomes 0. So the substance, the solution whose conductance is needed to be determined. In that, this conductivity cell is dipped, and the conductivity cell 2 arms are connected to the 2 arms of the Wheatstone bridge. Then, if we vary the variable resistance at one point of time, the current flowing through galvanometer becomes 0. At that, by using that condition, we can determine the resistance followed by conductance and other parameters. So, in the last video itself, I have discussed about specific conductance of a solution. Specific conductance of a solution. What is the specific conductance of a solution? Specific conductance of a solution is the conductance of 1 centimeter cube or 1 cc of solution. 1 cc of solution is called specific conductance. Is called specific conductance. What is specific conductance? Specific conductance is the conductance of 1 centimeter cube or 1 cc of solution. We can say it as a 1 ml also. 1 ml of solution. 1 ml of solution, we are calling it as the specific conductance. Then we have brought another word, molar conductance. Molar conductance, which is denoted with lambda or lambda. Here, molar conductance is the conductance of VCC of solution, VML of solution, VML of solution containing 1 mole of electrolyte. Containing 1 mole of electrolyte is called molar conductance. The entire solution is placed between the platinum electrodes of 1 centimeter apart, and area is VCC. Area is VCC. That one we are calling it as the molar conductance. Now we are going to discuss about what is the effect of dilution on conductance, specific conductance, then molar conductance, specific conductance and molar conductance. What is the effect of dilution? You see, generally we know that whatever conductance we are discussing is, that is, we know that electrolytic conductance, right or no? Here the whatever we are discussing is electrolytic conductance. We know that electrolytic conductance is due to flow of ions. Electrolytic conductance is due to flow of ions, whereas electronic conductance is due to flow of electrons, whereas electrolytic conductance is due to flow of ions. It is due to flow of ions. Here, the electrolytic conductance, as if number of ions are increasing, what happens to conductance? Increases. If number of ions are increasing, conductance is increasing. If mobility of ions also increases, conductance increases. By means of dilution, what happens is dissociation of electrolyte increases. What happens? If we dilute an electrolyte, what happens? Dissociation increases. Dissociation increases, which in turn conductance increases. If we dilute an electrolyte solution, dissociation of electrolyte increases, which in turn conductance increases, which is due to increase in mobility of the ions. So generally, conductance increases with increase in dilution. What happens to specific conductance? Specific conductance decreases with increase in dilution. Specific conductance decreases with increase in dilution. Specific conductance decreases with increase in dilution. Why it is decreasing? Decreasing, which is due to decrease in number of ions. It is due to decrease in number of ions per cc of the solution. It is due to decrease in number of ions per cc of the solution. So what happens per cc means? For example, let us assume I have taken 1 ml of electrolyte, 1 ml of solution. I have supposed that there are 100 ions. If I dilute it to, suppose 10 ml, by addition of the 9 ml of water, I have added to it 9 ml of water, then I have diluted 10 ml. Then due to increase in dilution, what happens? Number of ions are increasing. So initially I have assumed that 1 ml of electrolyte solution I have taken. I have assumed that 100 ions are present in that 1 ml. Now I have added 9 ml of water and I have diluted to 10 ml. Then what happens? Number of ions are increased to, let us suppose, some 500. 500 ions are present in 10 ml. Now, what is the number of ions per ml now? Here, 100 per ml. Here, what happens? 50 per ml. Right or not? 500 by 10. 500 ions are present in 10 ml. For 1 ml, how many ions are there? Only 50 ml. 50 ions are present. So, as number of ions are decreasing, its conductance, that is specific conductance, decreases with increase in dilution. Specific conductance decreases with increase in dilution due to decrease in number of ions per centimeter cube of the solution. Per centimeter cube of the solution. So initially 1 ml consists of 100 ions. If I diluted, what happens? Even though number of ions increases to 500 ml, 10 ml consists of 500 ions. So per ml, how many ions are there? 50 ions. That's why it is specific conductance decreases with the increase in dilution. Whereas molar conductance, what happens is increases with increase in dilution. Molar conductance increases with the increase in dilution. It is due to increase in the number of ions. What happens? Initially 1 ml I have taken, I have assumed that it consists of 100 ions. When I diluted to 10 ml by addition of 9 ml of water, what happens? 500 ions. See, that is the difference between specific conductance and molar conductance. Specific conductance is defined only for the 1 ml, whereas molar conductance is corresponds to the VCC of solution. So, for entire solution is placed between the platinum electrodes of 1 centimeter apart, and its area of cross section is corresponds to the whatever ml we have taken. So, entire ions will be present in that area. That's why it corresponds to 500 ions. Here, what happens is molar conductance increases with increase in dilution, whereas specific conductance decreases with increase in dilution. So this is the relation between specific conductance and molar, defect of dilution on specific conductance and molar conductance. Now let me discuss relation between specific conductance and molar. Specific conductance and molar conductance. We know that what is specific conductance? Kappa is equal to C into L by E. C into L by E. This is the formula we know for specific conductance. Now, what is the relation between specific conductance and molar conductance? Now, for example, let me take 1 ml of water and I have dissolved 1 mole of electrolyte. 1 mole of electrolyte. Then what happens? I measured, so I have taken 1 ml of water and I dissolved 1 mole of electrolyte. I dissolved 1 mole of electrolyte. Then what happens? I measured the conductance. Now, as it is the solution is corresponds to 1 ml, it is corresponds to specific conductance. Right or no? As it consists of 1 mole of electrolyte in VCC of solution, this is also corresponds to molar conductance, but both are equal. See, 1 mole of electrolyte, 1 ml of electrolyte solution containing 1 mole of electrolyte. This is gives the specific conductance as well as molar conductance, because specific conductance is defined for 1 ml. Molar conductance is defined for VCC of solution. V may be 1, 10, 100, maybe like that, but the solute should be, electrolyte should be 1 mole. So that's why what happens in this case, specific conductance is equal to molar conductance. Now I have diluted this to 4 ml by the addition of 3 ml of water. Now I have diluted to 4 ml. What happens? I measured again the conductance. Now what happened? 1 mole of electrolyte is present in 4 ml of solution. 1 mole of electrolyte is present in 4 ml of solution. I measured the conductance. Now what I will get? I will get the molar conductance because 1 mole of electrolyte present in VCC of solution. That's why what I am getting is molar conductance. Yeah. So here, when electrolyte is dissolved, if I divide it into 4 parts, this is 1 ml, this is 1 ml, this is 1 ml, this is 1 ml. I have taken 1 ml exactly. I measured the conductance. This is kappa. I measured the conductance here kappa. Because all 4 1 ml of solution containing equal number of ions as solution is here homogeneous. That's why what happens? This corresponds to kappa plus kappa plus kappa plus kappa. That's why I can write it as 4 into kappa. 4 into kappa. Now, this 4 ml again I have divided into 8 ml. Again, I have added another 4 ml. What happens? I measured again the conductance. What is it corresponds to? Molar conductance. Again, this is 1 ml, 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 all 1 ml. And it consists of same number of ions in all the 8 pots, 8 1 ml pots. This is 1 ml. Suppose if it consists of 10 ions, here also 10 ions will be there, here also 10, here also 10, here also 10, 10, 10, 10. That's why it's, if we measure the conductance of this 1 ml, it's always same as for all others. That's why I can write it as a 8 into. Suppose if I dilute it to VML, what happens? Now kappa is equal to, sorry, lambda is equal to kappa into V. So initially, if I have taken 1 ml of electrolyte, 1 ml of electrolyte present 1 mole of electrolyte. 1 mole of electrolyte is present in 1 ml of solution. There, molar conductance is equal to specific conductance. Here, the dilution factor is 1. If I dilute it to 4 ml by the addition of 3 ml of water, then what happens? If I measure the conductance, I am getting molar conductance. But it is equivalent to 4 times of the specific conductance, because number of ions are present same in the 4 compartments. Similarly, 8 ml, 10 ml, like this. If I dilute it to VML, then what will happen? Lambda is equal to kappa into V. Now we know that molarity is equal to, what is molarity? Molarity is equal to number of moles into 1000 by V in ml. Suppose he has 1 mole of electrolyte, N is equal to 1. 1 mole of electrolyte is present. What happens? N is equal to 1. So what happens? M is equal to 1000 by V. So we know that molarity is there. One of the method to determine the concentration of solution, I am writing in place of MC. That's why 1000 by V, which in turn V is equal to 1000 by C. So what I can write here, kappa into 1000 by C, where C here, don't confuse, C is concentration of the electrolyte in molarity, concentration of electrolyte in molarity. So now this is the relation between molar conductance and specific conductance. Molar conductance and specific conductance. So we know that formula for specific conductance is equal to C into L by A, whereas for molar conductance is equal to kappa into 1000 by C. Here C is the conductance. Here C is the, what it is? It is concentration of electrolyte in molarity. Concentration of electrolyte in molarity. So this is the relation between molar conductance and specific conductance. So we may need to solve some numericals by calculating specific conductance and molar conductance. Now let me discuss the electrolytes of. We know that electrolytic conductors are called as electrolytes. These electrolytes are classified into 2 types. One is weak electrolytes and second one is strong electrolytes. Weak electrolytes and strong electrolytes. What are weak electrolytes and what are strong electrolytes? Weak electrolytes means, the strong electrolytes means, we know that here if I use the word conductance, it corresponds to molar conductance. But the strong electrolytes means, this is, for example, we know that molar conductance increases with the increase in dilution. Molar conductance increases with the increase in dilution. So for a substance, molar conductance increases with increase in dilution. Increases with increase in dilution. After a dilution, its value is becoming constant. Its value is becoming constant. The molar conductance of an electrolyte increases with increase in dilution. At a particular dilution, it remains constant. Those type of substances are called weak electrolytes. Strong electrolytes. Whereas there are certain substances whose molar conductance increases with increase in dilution and never approach a constant value, keep on increasing. Those substances are called strong electrolytes. Weak electrolytes, strong electrolytes. Strong electrolytes means whose molar conductance increases with increase in dilution, and approaches a constant value at a particular dilution. approaches a constant value at a particular dilution. Those substances are called strong electrolytes. Weak electrolytes means the substances whose molar conductance increases with increase in dilution never approach a constant value. Never approach a constant value. Molar conductance increases with increase in dilution, increases with increase in dilution, and approaches a constant value. Approaches a constant value. Those substances, for those substances, molar conductance, those substances for which molar conductance increases with increase in dilution and approaches a constant value are called strong electrolytes. Whereas molar conductance increases with the dilution, increase in dilution, and never approach a constant value. Never approach a constant value. Are called weak electrolytes. So based on the molar conductance, what happens to dilution? The substances are classified into two types, strong and weak. Strong means molar conductance increases with increase in dilution and approaches a constant value. Whereas weak means the molar conductance increases with increase in dilution, but never approach a constant value, means keep on increasing. Keep on increasing. Those substances are called weak electrolytes. So all strong acids are and strong bases are HCl, H2SO4, NaOH, all are the examples for the strong electrolytes. All weak acids and weak bases are examples for the weak electrolytes. Weak electrolytes. Here, in strong electrolytes, the molar conductance increases with increase in dilution. At a particular dilution value remains constant. After this dilution, there is no change in the molar conductance. At this dilution, molar conductance remains constant. Afterwards, the molar conductance remains constant. This dilution is called molar conductance at infinite dilution. The dilution, molar conductance at infinite dilution is called molar conductance at infinite dilution. Thank you. In the next video, I will continue this topic. Thank you for watching Trinath chemistry classes. Please subscribe my channel, share, like the video. Thank you.